All right, so again, hopefully there'll be a few more join here shortly. First thing, just remind you, our third test is coming up Monday. Uh, same as first two tests, 11 o'clock. You can start the process a little before 11 is fine. But everybody gets 60 minutes from the time you actually get the test open and start taking it. So it just goes up through what we did yesterday. And we're going to talk some more about the test here shortly. But the first part of class, I want to start something new. We're going to skip ahead to chapter 11 and talk about beam design. Uh, so that's what we're going to do. The first first half of the class is again, you'll find what we're going to talk about today in your textbook in chapter 11, the first two sections. And excuse me, uh, it may seem a little strange we skip from chapter 7 to chapter 11, but personally, I think this fits better falling right after chapter 6 and 7 when we've been talking about bending stress and shear stress and beams. I think it's best to do this right after that while that's still fresh on your mind rather than, covering two or three chapters and then getting here. So that's why we're skipping ahead. We're going to go back to chapter 8 after we do chapter 11. It's also, I think, a very good, really kind of review for your test on Monday because you're going to see basically we're just applying the same things we did in chapter 6 and 7, but we're kind of going backwards. Whereas in chapter 6 and 7, you were given the size of the beam and you were calculating the bending stress and shear stress. All we're going to do in this chapter is you're going to be given what the allowable stresses are, and you have to determine what size beam is required so that you don't exceed those stresses. So we're using the exact same relationships and formulas. We're just going backwards. But kind of general piece of information, and then we'll work an example. Again, there's really not anything new to learn here, but just the general information or suggestion. Typically, what's done when you actually are designing beams, you find that the bending stress usually is more critical than the shear stress. Now, I'll emphasize here, usually, there's always exceptions, but the majority of the time, the bending stress is what's going to determine the size of the beam. So in the long run, you're better off design the beam uh, for bending. And by that, what I mean, we're going to size the beam so that our maximum bending stress is less than or equal to our allowable bending stress. So that's what we're going to use to determine the size of the beam. And then for the size beam that it takes to satisfy this, we check and make sure the allowable shear stress is not exceeded. So then check the shear stress for this size beam. And by that, what I mean is we're going to verify that the maximum shear stress is going to be less than or equal to the allowable. That's typically the the process that you go through if you're designing a beam. You design it for bending, check and make sure the shear stress is okay. Now, occasionally you'll find, oh, well, the shear stress is not okay. It's too big. Then you go back and obviously have to revisit it and size it to match or so that it doesn't exceed the allowable shear stress. But most of the time, that's not going to be the case. That's why, in the long run, it's less work to go this route rather than the other way around. All right, so let's look at a beam, and here we're given the allowable normal stress is 2 ksi. The allowable shear stress is 1 ksi. And we're going to find the minimum dimension B, I call it. So what we've got is just a simply supported beam with pin support this end, roller at the right end. It's 6 feet long, and we've got a constant distributed load. Runs the entire length of the beam, and this is 1.5 kips per foot. All right, so that's the beam, how it's supported, and the loading that's applied. Our cross section is just a rectangle. So this is, again, here, this is what the cross section looks like. It's rectangular. The width, that's what we're trying to determine. We're trying to decide how wide this cross section has to be, right? So that we don't exceed those two allowable stresses. The height is given is 8 inches. All right, so this is our problem. We've got this beam, we've got a rectangular cross section. We're going to design this beam or size the cross section so that we don't exceed those two allowable stresses. All right, well, we're going to need to know what the maximum shear force is, because we need that to check the allowable shear, to check the maximum shear stress, and we need to know what the maximum bending moment is in order to determine what the maximum bending stress is. So this is exactly what we did. The first of chapter 6 is we need to draw a shear moment diagram and determine what those maximum shear force and bending moment are. We got support reactions, AY, BY. And again, just remind you, the pin supported A is capable of a horizontal reaction, but we don't have any horizontal forces, so AX is 0. Now, we can get AY and BY pretty easy just from symmetry without having to do a lot of calculations. Our distributed load, remember the resultant force, is just equal to the area. So we got 1.5 times 6. If I do my math right, that's 9 kips. So that distributed load is equivalent to a 9 kip force, and it acts at the centroid, which for a rectangle is right in the middle. So this is going to be right in the center of that beam. And so just from symmetry, I know AY and BY are going to be equal, and they're going to be half of 9. So each one of these is going to be 4.5 kips. 4.5 kips. And now we can draw our shear and moment diagrams. And again, this is something you might be asked to do Monday on your test. So this is why this is a good review. So for the shear diagram, again, make sure you put units. These are forces in kips. So we're going to start at whatever AY is, which is 4.5. And remember, it's 1 degree higher. So if our distributed load is constant, shear is going to be linear. Right? We're going to go down a total of 9 kips. So we're going to go down to negative 4.5. And it's going to be linear. So I'm going to attempt to draw a straight line here. Yeah, it's pretty straight. Right, so that's what the shear diagram would look like for this loading. And now we draw the moment diagram. Again, remember to put units. These are kip feet. Now remember, the moment diagram is based on what the shear diagram looks like. We go up or down, whatever the area is, under the shear curve. So in this case, we're going to go up because it's above the axis, positive area. We're going to go up whatever that area is. Well, that means we need to know what this distance is. We need to know where it crosses. Now, this one, just from symmetry, I can tell you it's going to cross right in the middle, halfway at 3. So if you can determine that from symmetry, that's great. But in general, it's not always going to be that way. If this distributed load didn't go all the way, the entire length of the beam, and we had some other stuff going on, it wouldn't necessarily cross halfway. But so just, if you are not sure about, whether or not due to symmetry it's going to cross halfway, it's real easy. You can use similar triangles, right, and determine exactly where it does cross. If you look at our big triangle, this is 9, and we go across 6. So we want to know if we go down 4.5, how far is that across? And if you do similar triangles, x is to 4.5, s6 is to 9, and you're going to get x equals 3. So if you're not sure, it only takes a second. Do similar triangles and make sure. But this is 3 feet. So it's going to cross. So to get our area, A1, it's a triangle. So it's just 1/2 base times height. So 1/2 base is 3, height is 4.5. And I got 6.75. So we're going to go up 6.75. Now what the graph looks like is 1 degree higher. If the shear force is linear, this will be quadratic. So it's a curve. And we also know it's going to be concave down because B is decreasing. So it's going to start at 0, right? Important. If you look at the end of this beam, we don't have a moment. So it's going to start at 0. It's going to be a quadratic, a curve. It's concave down. Now, just observation, A2, the same magnitude as A1, right? It's just negative. A2 would be a negative 6.75. So we're going to go down that amount, which, fortunately for us, does take me right back to 0, which is what it should be, because there's no moment at the right end of the beam either. All right, so now that I have my shear and moment diagrams, I know Vmax, and we're just looking for the largest magnitude here. And in this case, the largest positive and negative, the same. It's 4.5. These are kips. Maximum bending moment. Again, you would choose the largest magnitude here. Doesn't matter, positive, negative. We want the largest magnitude. In this case, it's positive. It's 6.75. Those are kip feet. So I know what the maximum shear force is. I know what the maximum bending moment is. So remember, we're gonna size the beam to satisfy bending. Remember in chapter 6, we had this, in general, it was minus my over I, but here we're just looking for largest magnitudes. You want to use that formula MC over I. Was the formula for the maximum bending stress. So what we're going to do is set this maximum bending stress equal to our allowable, and we're going to solve for B, the dimension there. Now this I, that's the moment of inertia about the neutral axis. So this is also good review for tomorrow, or not tomorrow, Monday. The neutral axis, remember, is the axis, the horizontal axis that goes through the centroid of that area. That's where the neutral axis is located. And we also know for a rectangular cross section, right, I is 1/12 base times height cubed. That's one of the other things I told you you're responsible for on Monday. So again, it's 1/12 base times height cubed. So 1/12, our base B, that's what we don't know. The height is 8. So that's my moment of inertia. For this particular cross section, remember C here is, it's just the furthest distance you can get away from the neutral axis. It's the absolute value Y max, which for our problem is 4 inches. Right? Our cross section is 8 inches tall. That would be 4. And it'd be the same to the top and the bottom. That's why it doesn't matter if you go, if one was larger, use the larger one. So let's set our normal stress equal to our allowable, 2 KSI. Be careful with units here. If we leave that in KSI, that's okay if our moment here is in kip feet. But you couldn't have, say, PSI and kip feet, or have KSI and have pounds feet. So just be careful. But we do need to convert this into kip inches, because everything else is in inches, right? This is KSI, kips per square inch. C is in inches. This 8 is in inches. Everything else in inches. So we want to multiply our 6.75 kip feet times 12. Right? So that's going to give me inches. That's why I'm multiplying by that 12. And C was 4. I 1/12 B times 8 cubed. And then solve for B. Skip going through all the math. I got 3.8 inches. B is equal to. Right, but we're not quite done, right? That would tell me what size beam I need to satisfy the allowable bending stress. Most of the time, we'll find the shear stress is okay, but you've got to check the shear stress for that size, right? So we need to make sure that we check tau max for, again, B equals 3.8. Again, if you don't do this, you could really set yourself up for, in the real world, failure, because occasionally it doesn't work out, and the maximum shear stress actually is what determines the design. So you got to check it. So remember, for a rectangle, this was also another thing that we went over in chapter 7, right? So remember, for if we had a solid rectangle, I'll put it down here. Got a solid rectangle. We found tau max was 3/2 V over A. Now again, I mentioned when we did this, it's up to you whether or not you remember that formula or not. If you do, it comes in handy when you do have a rectangular cross section. You don't have to calculate what Q is. And we've already calculated I, so basically all it does is save us having to calculate Q. But for a rectangular cross section, finding Q is not real difficult. So yeah, if you don't remember this formula, right, you could always use tau equals VQ over IT if you happen to not remember that for a rectangle. So what we're going to do is we're going to see what tau max is for this cross section if B is 3.8. So tau max would be 3/2. V max was 4.5. That's V max. And the area, it's a rectangle. So if B is 3.8, what's 3.8 times 8? Right. So we put in our B and see what tau max is. And I got 0.22. And this would be KSI since our force is in kips. And that is indeed less than the allowable. Right. So our maximum shear stress for that size beam is less than the allowable, right? Which was, again, this was 1 KSI. So we know now use B equals 3.8 inches. All right. So any questions about something in particular or the general process there? Again, it's using a lot of the same things we've been doing in chapter 6 and 7. It's just difference is here we know what stress or we can't exceed. What size beam do we need so that make sure that doesn't happen? All right. Anything else about this example? Right, now we're going to continue with beam design, I reckon, Tuesday next week after our test. And starting on Tuesday, we're going to kind of focus on or put more attention on selecting what we call standard size manufactured beams. So I just want to take about 5 minutes and just kind of tell you what that is, and then we'll stop and then we'll talk about the test coming up. All right, anybody need another second or two, or everybody got everything for this example so I can get a new sheet? All right. So again, just a couple minutes, talk about standard size manufactured beam. And so that the example we just looked at would be more fall under like a custom made beam, right? We were custom sizing this beam, but there are a lot of standard size beams that steel manufacturers produce that you can go pick out or select from whatever vendor you're buying from. This standard size beam, and typically, especially when you're talking about steel beams, it's cheaper to buy a standard size beam than it would be to have a custom made, custom size steel beam made. If you're building a building and you're going to be using, buying 500 of these beams, you're not going to want to pay for 500 custom made beams. You're going to go pick a standard size beam. It's a lot cheaper, right? And there's an appendix in the back of your book. and they're much more extensive list out there. This is just a shortened list that the publisher put in the back of the book. So you have some knowledge and you've seen this before, but especially the civil engineers, if you haven't encountered the AISC manual yet, there's some much more extensive list of standard size beams in there. But I think, hang on, I copied. So this is a copy of one of the pages out of the back of the book in Appendix B. You'll see what we call wide flange I-beams. There, I think, are C sections. Cross sections look like a C. There are angles. The cross section looks like L's. And there are tables for English units, and there's tables for SI units. But this is just an example of what's back there, and you'll see these are all different names or designations for these standard size beams. So you could, call up your steel manufacturer and say, I want a W12 by 87 beam. They've got the whatever molds, forms necessary. They can manufacture these with what they have on hand, and it's cheaper to buy a standard size beam again than have one custom made. All right, so all I want to do left here is just talk about what this designation, what these numbers and symbols mean. So, for example, let's just take this top one here, W 12 by 87. Okay, so I'm going to come back to that table in a minute, but so let's look at a W12 by 87. So the first thing, that first letter, that tells you the shape. What cross section is this beam? So W here stands for a wide, if I can spell this, wide flange I-beam. That's what the W tells you. Now, again, I mentioned in the back of the book that there's a table. If you got a C, that's going to give you a cross section. Looks like a C. There's an L and then some numbers, right? That's an L-shaped cross section. Now, one that's not in the back of your book that's fairly common. There's an S-shape, and it's an I-beam, but rather than like when it says wide flange, you're thinking about a shape like this. An S-shaped I-beam, the flanges are shorter and thicker. It almost, to some extent, kind of looks like maybe like a whale's tail, maybe. And then you'll see, I don't know, this is not a great picture, but it's something like that. It's an I-beam, but you got shorter and thicker flanges. This table's not in the back of your book, but you will see they're fairly commonly used shape. All right, so the first number, in this case, this is the nominal, I can spell nominal, excuse me, nominal depth. And by nominal, I mean, I can squeeze this in here, approximate. So this first number tells you approximately how tall this thing is. But notice, again, it's just an approximation. So it's a number. If you're designing something, it gives you an idea about how tall this beam is going to be. If you want the actual depth, you got to get that number off of the table. In fact, if we go back and look, for this first one, this W12 by 87, the actual depth, the height of that is 12.53. So just note here the actual depth comes from the table. And for this one, it's 12.53 inches. Right, so it's not exactly 12. Right? There we go. All right, but that's what the first number tells you. This is approximately how tall this beam is. Right? And then finally, I will say this. If you're doing English units, this is going to be in inches. Or if you're doing using the table for SI, it'll be in millimeters. So if we were doing looking at the table with SI units, that would tell you the approximate height in millimeters. All right. So finally, this last number, in this case, 12 by 87. What that number gives you is the weight per foot, or again, if you're doing the SI units, it would be kilograms per meter. So that's what that last number tells you, is how much this thing weighs, essentially. Now, what's important about that last number is basically that's going to tell you the cost of the beam. When you buy steel beams, basically you're paying for the steel. So it really doesn't necessarily matter so much what shape it is. What you're paying for is the steel. So that last number out there tells you for this beam, this thing weighs 87 pounds per foot. And so the bigger that number is, the more it's going to cost. You're paying for more steel. So if you look back at this table, the one right below it, the 12 by 50, it weighs 50 pounds per foot. That's considerably lighter, and it's going to be cheaper. Right? So that's what that last number tells you is, again, kilograms per meter or pounds per foot. Again, this would be in pounds per foot if you're doing English units. All right, so let's just get some terminology out of the way, because that's what we're going to look at Tuesday. Is instead of like custom designing that beam like we did in the example today, we're going to be selecting and picking one of these standard size beams. And there's a bunch of beams that would work, but we want to pick the best beam. Right? We want to be good engineers. That's what good engineers do, is pick the best beam, not just first one you come to that works. All right, but that's what we'll pick up on Tuesday. Any questions at this point about designing beams? All right, so let's focus on our test coming up again. Again, same process, procedures before. I'll see if I can find the email I sent you last time, and I'll send that out again sometime this afternoon, just as a reminder of the steps to follow. Also, same general advice as always. Make sure to show me all your work, especially. I'm only going to grade what you scan and email to me, so keep that in mind, and don't forget anything that you want me to grade has to be on what you scan and email back to me. There's 4 problems, just like the last test. 4 problems. As always, make sure you put units on your final answer. Same as first 2 tests. It's closed book, closed notes. There's no formula sheets. So just your calculator, and those are the only resources you got to work with. All right, so I think maybe what I'll do is, there's basically just 4 sections that we did, right? Basically, this is what I call the beam test. All we did was we drew shear and moment diagrams for beams. We calculated bending stress. We calculated shear stress in beams. That's what this test covers. And again, it's chapter 6 and 7. We did 2 things in chapter 6. In the first couple of sections, we talked about how to draw shear and moment diagrams. And remind you, emphasize here, I want you to do or use that graphical method. If you try to cut the beam and get the equations for V and M, I can tell you, you're not going to have time to do all 4 problems. But it's not necessary. We can do it a lot quicker and easier using those graphical methods. That's what I want you to do on the test Monday. All right, so we'll kind of go through and we'll just in general, and then we'll come back, and if you got specific questions, we'll address that then. But that's going to be something you're going to have to do Monday, is you got to know how to draw a shear and moment diagram. Then the other thing in chapter 6 we talked about was bending stress. And we had this formula, sigma is minus my over I. So definitely you need to know that. One of the other formulas that you may want to use, we actually used a minute ago, right? The sigma max equals MC over I, where, again, C here is just the largest Y value, Y distance you can get. So the largest vertical distance away from the neutral axis. Remember the neutral axis, that's what I is. This is moment of inertia about the neutral axis. M's the bending moment. That's how you calculate bending stress, or normal stress due to a bending moment. Remember the neutral axis is at the centroid. So if it's an isometric area, like the example we worked at the beginning of class today, use symmetry. You know, if you can use symmetry and you know the centroid's right in the middle, do so. I get real, I don't know, sort of frustrated sometimes. I see students that they'll say, you know, I didn't have time to finish the test, and when I'm going through and grade it, and then they spent probably 5-10 minutes calculating the centroid location that they could get just by looking at it. And so if you don't have to calculate where the centroid is, don't, right? Use symmetry. Now, if you can't use symmetry and you have to calculate it, then remember that was the formula to locate where the centroid of an area is. You know, break it up into 2, 3, 4 pieces, however many, and get the area of each piece, locate the centroid of each piece, multiply the area times the distance to the centroid, divide by the total area, now locate the centroid. That's where your neutral axis is going to be, right? And that's one of the first things you got to do on all these problems, because everything is dependent upon, you know, distance away from the neutral axis. So you got to find where the neutral axis is. It's at the centroid. And then one other thing that we ran into a minute ago as well. I told you one moment of inertia formula I expected to know was for a rectangle. And if this is the z-axis that goes through the centroid, that is our neutral axis. If it's got some width b and height h, I told you I expect you to know this one, that moment of inertia about the axis through the centroid was 1/12 base times height cubed. Right? Any other shape beside a rectangle, I told you I would provide that table that's in the back of the book. Right? So just remember, any other shape you're not responsible for, any other shape, that table would be provided. So I don't expect you to know what the moment of inertia is about the axis through a circular area or a semicircular area. If you ran into something like that, it would be provided. Just the rectangle, that one I expect you to know. And then you also need to know how to apply the parallel axis theorem. Right, so if you're getting the moment of inertia about the neutral axis and it doesn't go through the centroid, say, of that piece, then to get the moment of inertia about the neutral axis or the z-axis that you want, you take the moment of inertia about the axis through the centroid, like 1/12 base times height cubed, and you have to add AD squared. Where that D is the distance from the neutral axis to the centroid of that piece. Right? And again, this is nothing new. You should already know how to find a centroid and how to apply the parallel axis theorem. So hopefully you do. If you don't, make sure you know how to do that before Monday. Right? And that was chapter 6. And then in chapter 7, we did shear stress. Right? We had that formula, tau is equal to VQ over IT. Right? You know that formula. Right? And we spent some time discussing about how to know where the maximum shear stress occurs. Now, it's going to occur where Q over T is a maximum. V and I are constant with respect to the cross-section, but Q and T change. And what I told you was, look and see, does the minimum thickness occur at the neutral axis? So remember, if T min is at the neutral axis, then that's where tau max will be. Right? And this is since Q at the neutral axis is the maximum Q. So at the neutral axis, if Q is max and T is min, that's going to give you the largest ratio of Q over T. So always look and see if that's true. If it is, that's where your maximum shear stress occurs. So you need to find Q at the neutral axis. Now, to calculate Q, notation the book uses is A prime times Y bar prime, where A prime is the area above that point on the cross section, and Y bar prime is the distance to the centroid of that area, A prime. And then if you want, and you may or may not need this, but for, I'll just remind you, we used this just a minute ago. For a solid rectangle, tau max was 3/2 V over A. So if you encounter a problem with a rectangular cross section, like that first example we did, and you want to use that, it'll save you a few minutes. Right? But otherwise, that formula always works. And then there's only one other thing we did, and that was what we did yesterday, and that was look at the built-up beams. Again, this was shear stress. And we had that formula. This is the shear force on each fastener is BQS over I times the number of rows. Again, the Fs is the shear force on each fastener. B is our internal shear force. Q, same as it was up here in this formula, but remember here, Q is for the area A prime that's attached by the fastener. And so in this formula, that's the Q you're going to use. Is if you got, we looked at an example, we had a box beam where we had this board nailed on top. So Q is for that area A prime that's attached by those nails. S was the longitudinal spacing between, if you go down the beam, the spacing between the fasteners. I is the same as always. And again, if you got 1 row, 2 rows, 3 rows, all it does is divide the force on each fastener by 2 or 3 or so. That's it. That's what we've done in chapter 6 and 7. What you're responsible for on Monday. Again, you're going to be asked to solve 4 problems. So the more problems you work between now and Monday, or hopefully have been working on, the better off you're going to be on Monday. Problems, they're going to look similar to what you've seen in the homework problem. So, questions?
Yeah, I got a question for all of us.
Okay.
All right. First off, is my audio all right this time?
Yeah, I can hear you fine.
Hey, wonderful. All right. So for the parallel axis theorem,
Correct.
where we have to do the base times height times the distance squared,
Yes.
what separates that from when we would just have to use a regular I equation?
But it depends on, say, for example, let me get a sheet of paper here. All right, so say, for example, like we just have a rectangular cross section like we did in that first example. Right? So we know the neutral axis, right? It goes through the centroid of the whole thing. Now, in this case, the centroid of the whole thing corresponds to the centroid of this piece. So maybe we'll call this, like, say, C1. They coincide. So if let's say this is base and this is height. So here it would just be 1/12 base times height cubed. And that's it, because the centroid of that area is on the neutral axis. Right? But if we had, say, the same thing, now we got 2 pieces. Right? The centroid for the whole thing is going to be located down here closer to the bottom. And so that would be the centroid for the whole thing. That's where our neutral axis is. Right? But we would need to calculate where that is, right? So that's where we would use this formula to locate where that centroid is. But the centroid here, say, we'll call this A1, A2. The centroid for that is not located on the neutral axis, right? Same thing up here. This centroid is not located on the neutral axis. So if we want to calculate what the moment of inertia for the neutral axis is, right? When we would do, say, for area 1, we would do, whatever 1/12 base times height cubed for that rectangle. But this is some distance. Make this long. This. That's what the D is. The distance from the centroid of this piece to the centroid of the whole thing. That's where we would have to add whatever that area is times that distance squared. And then we have to do the same thing for area 2. Say 1/12 base times height cubed for, let's see, this is B2 and H2. But again, the centroid of this piece is not located on the neutral axis. Right? It's some distance away from that neutral axis. So we'd have to add the area times that distance squared. All right, so does that clear that up?
Yes, sir. Thank you.
Uh-huh. All right, other questions? All right, well, our allotted time is up, so I'm going to stop recording, but everybody's welcome to stick around if you want to, and we can continue with additional questions, but I'm going to stop the recording. Give me just a second.